solve another fluid dynamics problem. It's going to be a very long one. Incompressible Newton flow is daily between two infinite long and cylinders as shown in this picture. The outer cylinder is fixed, the inner cylinder moves longitudinally with V naught. What is the value of V naught? To have, that's our key thing. We don't want drag, right? So we get drag from shear. Shear, it's like two things sliding against each other. So if we don't want this thing to slide, this rod to slide against this fluid and then cause friction. So that's what drag is, think. So we know that shear, the face that we're interested in, it's an R sphere. Because if I look at this thing like this is literally right around the radius. So you don't want shear as much. When I pull this thing, I want to be freely pulling this thing back and forth. Right, this is the thing I'm talking about. We want to be able to pull it like this and forth without having any drag. Right, so I'm going to do an outline of a problem just to make sure that even if I don't finish to solve a problem, but at least I explained how you expect it to solve. Shear on the R face in the Z direction should equal to mu, of which that's a material property, dVr all over dz plus dvz all over dr. Yeah, so we're trying to make this thing goes to 0. That is our goal. So before we do that, this means you need to know what are these guys. For us to achieve that, you need to know what are these guys, right? So let's try solving the problem. So at least you know this is your end goal. Let me put it in bracket. We'll come back to you. Hopefully we do. End goal. Okay, we have our guy here. Let's keep him here and try to solve. So you have to do the whole trying to find how this thing looks here, like it will look something like that, but I don't have to do it because I've done it before. So we know a solution for a tube, the distribution of the velocity longitudinally. We know a solution. We said V along Z is equals to 1 over 4 mu. It's quite easy to memorize because for some reason it's just easy to memorize. 1 HR. Then let me call this equation 1. This is our solution. This solution, you can do it from cancelling all your terms in Bernoulli's and all that. We could do that, but it will make a video long while it's already long enough, right? And then after that, we apply boundary conditions. If we apply boundary conditions, we're going to say when R is equals to Ri, that's here we're interested in. When we are on the edge, what is going to be our V? Is going to be V naught, right? And then if we apply that there, we're going to go there, plug it in. We're going to add V naught here as our answer, 1 over mu, 1 over 4 mu dp dz. R now is going to be Ri plus C1. Oh, that's lean. I don't know how it didn't look like lean. Why I'm writing English lean? Lean Ri. I'm substituting plus C. Let me call that C2. Right? Let me call that on 3. Let me try another boundary condition. Let me say let me do a blue one. A blue one is saying when I'm on this edge. So when my R is equals to R naught, what is going to be my v, my v is going to be 0 because the walls or the outer tube is fixed, on the inside one is moving. So we're going to have 0 is equal to 1 over 4 mu dp d dz r, that was squared there. Now it's going to be r naught squared plus c1 ln r naught plus c2. So we can just subtract these two equations. This is equation number 4. We can subtract them and have a good solution. So we'll have v naught is equal to, and then if I subtract them, are you doing that, is equal to, don't do that, and then here I'll take a common factor. 4 mu dp dz is the same for everyone. Then this one is a negative one, so I start with ri squared minus r naught squared close plus c1, take a common factor again, use laws of logarithmics, then the positive one become on top, ri all over r naught. Then if I subtract this one, these are the same, I'll have nothing. So from here we want to find c0, c1. So it looks like it's something we can actually achieve. Hope it doesn't get long enough. Then if I try to solve that, I'll end up having c1 is equals to v naught minus 1 over 4 mu dp dz ri minus r naught, they're all squared, all that divided by ln ri all over r naught. So that is our constant. So we're not going to be interested in, you'll be asking why I don't do also c0. The reason why I'm not interested in c0 because if you go back here, we're interested in derivatives. So if I derive this solution, it's most likely I'll lose the last coefficient. So I'm going to lose c0 anyway, so it's not really significant for our solution. Okay, let's continue. So if you look here, we want our let's differentiate our thingy in terms of z to find this sum, right? So with is it z or r? It's r. Okay, fine. What is our actual solution? I think it looked like, let me say v at some r is going to equal to 1 over, don't calculate please, you're not doing well, 4 mu dp dz r squared plus c1. Let me, is this thing, I don't want to write it again, let's just keep calling it c1. I know we know it, just make things not look nice. Ln r plus some c0. If I differentiate this thing in terms of r, then this one will go down, I'll end up having 1 over, if I'm doing things the right way, I'll end up having 8 mu, then I'll have dp dz of r alone. Professor Dave explained. Plus c1 will remain, but if I differentiate this, will become r alone. Then now we lose this constant, so that's why we're not interested. So what we want, remember, let me just bring this term here also. It looks like it'll be useful. This guy. why are you taking in everything? Okay, I'll just rewrite it. It's saying that shear on the r face z direction should equals to mu dr dz plus dr dvr. Yes, like that. We already know this guy, and this guy is going to be 0 because there is no change in this in velocity. Let me think. I don't think both of them were VRs. I don't know if, let me see. Yeah, the original thingy was VZ. This was VR. Yes, because yeah, I remember they were swiping. If you notice that pattern, this is same as that, same as that one. So yeah, now I'm fine. So radially, this thing is not moving like that. So that's why this term goes to 0. It's fixed radially, but it's moving back and forth, but not revolving, if that makes sense. So this is just going to be mainly that dv z dr, and we already computed this guy. This guy is him. Then we say d, we want this thing to be 0, right? Remember, we don't want drag mu, and then we bring that guy there, 1 all over 8 mu dp dzr plus constant 1 all over r. I think now it's time that we go find that constant that we don't like. Okay, let me take it. I don't like it too long, but looks like we are going to need it. So this is our constant. So let me copy everything here. I think I'll have to restart. This constant is very big. Okay, then I'll have v naught minus 1 over 4 mu dz r I minus r naught squared all over ln ri all over r naught. Remember, we are dividing with r here, so it will multiply by, we just multiply by 1 over r. So our next goal will be solving let me just put this r here. Our next goal will be solving for this guy, because we want a velocity where there is no drag. So what is going to be the velocity that you move the inside part? So from here it will be you solving this guy, and I don't know where you end up, but I hope that you end up with something that look beautiful as this. It's not going to be hard. I think we've tackled all the hard parts. No, don't compute. It have to look like something like this. I think you can see that it's possible, considering that we didn't make any mistake. That's ri squared ln ri r naught. So you see the term, I don't know how it ended up there, minus ri squared minus r naught. This is all under bracket, this is squared all inside the bracket. So this is your solution. So the moral of the story is that if you don't want drag, you bring this guy in shear. You want to push shear to 0, and then this solution, for test purposes, I think you should memorize it, but you can derive it if it would take longer. I think you won't be even awarded for it. Then you try to solve for C. Don't worry about the C in the end if you're going to differentiate in the end, because it will be not significant. Thank you.